Welcome back to Non-Equilibrium Thermodynamics, class number 5. Today we're going to talk about a reformulation of Euler's equation and the Gibbs-Duhem relation. And we're also going to look at something that we started looking at last time, um, molar versions of the thermodynamic equations. That is, equations that are written in terms of entropy per moles, energy per moles, volume per moles, etc. We started looking at this last time. We didn't get too far into it, so we'll start here and go in depth now. The starting point is the equation or the fundamental entropy relation. We could start with the fundamental energy relation as well. To keep things simple, we're going to consider a unary material. So that means that the number of species is exactly equal to 1R. Now, we can generalize to more species, but it just gets a little, it's not so clean, and so we'll use this very simple case. So unary material, looking at the entropy, the fundamental entropy relation, and we're going to assume by, or start by assuming that the number of particles is fixed. Okay, the number of moles of particles is exactly fixed. So suppose we have 2 moles of particles in our system, exactly that number, fix that positive number. And now we're going to define a few quantities. So the energy per mole is lowercase u, energy per mole. The volume per mole is V over N. Okay, it's also called the molar energy and the molar volume. And now, since the entropy is a function that is homogeneous of degree 1 for any lambda positive, we have this relationship. So this is the definition of what we mean by homogeneous of degree 1. And of course, in the thermodynamic setting, this is important because this tells us whether or not a variable is extensive or not. So the entropy is an extensive variable, otherwise known as an additive variable. So now we can switch, or we can use a particular value of lambda, and so the value that I want to use is exactly equal to 1 over n. If I use my homogeneity relation, then this is my, if 1 over n times the entropy is equal to the entropy of each variable divided by the total number of moles, which is fixed. And of course, now I see that this variable is just equal to my molar energy. This variable now is equal to my molar volume. And of course, this variable vanishes. It just becomes 1. All right, so now this is a particular function. And so I'm going to give it a name. I'm going to call it lowercase s. And of course, it's only a function of 2 variables, u and v. So that's exactly how I define this lowercase s variable. But it follows very quickly from this relationship and the definition of my lowercase s variable that I have this relationship. Very simple conclusion there. And likewise, I can do exactly the same thing for my energy. So if I define the following independent variables, the molar entropy, this is entropy per mole, and again, the same molar volume, then I can define lowercase u, a function only of the 2 variables s, lowercase s, and lowercase v, and that is equal to uppercase u of s, v, and 1. Of course, this is it appears like it's a function of 3 variables, but it's only, of course, 2. And by the same argument, uppercase u of s, v, and n is equal to n times lowercase u. And I'm going to keep the, at least for now, until it gets untenable, we're going to keep using the same sort of notation. The tilde means a function of other variables, and without a tilde, that means it's an independent variable. So we're going to have to abandon this after a while because the thermodynamic variables just start to pile up and it becomes too complicated. But for now, just so that we can make sure that everyone understands what's going on with these thermodynamic variables and the changes of variables that we're always doing, we're going to keep this notation going. So the best thing to understand, or the best way to understand new notation and new ideas, is with an example. I think this is the one we keep using over and over again. Let's use it again. S, U, V, and N is equal to this relationship. Of course, what we're looking for here is the fact that S satisfies the usual thermodynamic um, uh, principles or postulates, right? So that we want S to be a function that's concave. We want it to be an increasing function of U. And we want it to be where the temperature is equal to zero, that the entropy should also be equal to zero. So these are the basic postulates for S. These parameters R, V naught, and theta are all constants. And now all we're going to do is substitute in for U, V, and N, lowercase u, lowercase v, and 1. And of course, this gives us the variable, the dependent variable S tilde. That's equal to this function. Now, if we look at this function, we know previously the capital S tilde function is homogeneous of degree 1. What do we know about this function? Is it also homogeneous of degree 1? Well, it looks like if we put in lambda times u for u and lambda times v for v, right, we get lambda v here and lambda u here, so that's a lambda squared. Take the square root, we get 2/3. So this function is no longer homogeneous of degree 1, all right? So we've changed the nature of this function, so it's no longer homogeneous of degree 1. Now, we said that we had relations like this. If we multiply lowercase s by capital N, we should get back to s. Let's try that. If we do that, then we bring an n cubed inside of this power 1 over 3. We can distribute two of those to the v and the u, and of course get these variables, and so this just gets us right back to s. So this confirms, with a very simple example, nothing earth-shattering here, that all of our definitions make sense. Now, U tilde and S are, of course, homogeneous of degree 1 functions. These are extensive variables. Very important that we understand from the beginning that these functions have this property. It's very useful to us in terms of in our thermodynamic setting. Now, the derivatives of these functions, T, P, and chemical potential mu, on the other hand, are homogeneous of degree 0. Now, we stated this in a theorem, and we've shown it with a number of examples, but we've never, we didn't prove it. I left this up to you as an exercise. I hope that you see it's rather a simple exercise. But in any case, we're just going to use this fact without going through that rigorous proof. Tp and mu are homogeneous of degree 0 functions. So what does this mean? So this means for any lambda positive that T of S, V, and N is exactly equal to T of lambda S, lambda V, and lambda N. In other words, if I put in lambda times S, lambda times V, lambda times N, that lambda ends up disappearing. Okay, I think we've shown this with an example previously. It's not too hard to see. So now we're going to make a very simple realization, and that is that if I use lambda equals 1 over n as we did previously, then in this slot we get the molar entropy. This slot we get the molar volume, and here we just get 1. Now this function here, we can continue in the path that we've been going before. We could give this a new name. For example, we could call this lowercase t, in the same way that we used lowercase s and lowercase u previously. However, this is getting way too tedious, and so we're not going to go into to this level of depth, that's because we would have to make a lowercase mu, for example, and mu doesn't have a very good lowercase, so we're going to avoid that. And then, of course, lowercase t looks like time, and it's just going to get too tedious and too messy. So we're just going to understand that if we're using two variables, s and v, then this just means this object here. Okay, so we're just going to use this definition. I guess I failed to write it. We're just going to use t, in this case, u, s, and v is equal to tu of s, v, and 1. All right. So when we go from three variables down to two, it's just understood that that last entry is just a 1. Okay, so we're not going to change notation here. We're going to stick with our current notation. Okay, so this, like I said, is just going to be written as okay, and in a obvious abuse of notation. Okay, so now the next thing we want to do is derive Molar, Euler, and Molar Gibbs-Duhem relations, or Gibbs-Duhem equations. This is fundamental for us because this allows us, well, this is the practical way that these equations are most often used, as we'll see with a couple of examples. So let's first start off with the Euler equation. So for a unary material, the Euler equation for in the energy form or for the energy function is just U is equal to T times S minus P times V plus mu times N. This is sometimes it's called the integrated form or the Euler equation. This is the standard version of it. So now, suppose that N is a fixed number of moles and divide both sides by that number. So on this side, we get 1 over NU, of course, S over N here, V over N here, and the N over N produces a 1, which disappears. Of course, we'll immediately convert this to lowercase s, lowercase v, and this, of course, is just equal to, by our very simple relation, this is lowercase u tilde of s and v. Now, here, what do we do with this variable here? Well, we can immediately replace this with that, and then we're going to use our abused notation. So this term simply becomes tu lowercase s lowercase v. Same with p, same with mu. There's no difference really there with those variables. All that we're using here is the property that those are homogeneous of degree 0 variables. Okay, these are homogeneous of degree 0. So this gives us right away a version of the Euler equation, which is completely in terms of molar quantities. Molar quantities means per mole quantities. Okay, per mole quantities. Now, I don't know how universal this term is molar for per mole quantities. I'm not used to this notation. I'm borrowing it from the book by Herbert Callan, and he seems to use it for this case. But in chemistry, they may use another term. But it is obviously better than saying per mole every time, per mole. So we're going to call this, in keeping with Callan, our molar Euler equation. Molar version of Euler's equations. How do we get the Gibbs-Duhem equation? So remember the process for getting Gibbs-Duhem. So we start with, we formulate the molar version, or not the molar, but we formulate Euler's equation. Then we look, we take the We take the derivative of both sides of the Euler equation. We use the differential form of the first and second laws, and we subtract the two, and that gives us the Gibbs-Duhem equation. So we're going to try the same exact procedure, but using the molar forms. Okay, that means we need a molar version of the first and second laws of thermodynamics. Okay, also called Gibbs relation. So how do we get that? Well, let's look at let's look at this variable here. So if I look at that that dependent variable u, s, and v, so let's let lambda, or not lambda, but gamma of tau be a path in molar state space, which has the following form. It's just s of tau, v of tau. What does it mean to be a path in molar state space? Well, it just means that we're going to parameterize s and v, and we're going to do this in such a way. Well, you might as well just think about these as being just smooth functions of this process parameter tau. We're going to substitute that in here, and then we're going to take the tau derivative of that, okay, and see what we get. Well, we know that this is a function of two variables, right? And so it's very easy to take the tau derivative of that. That just requires using the chain rule. So by the chain rule, after I substitute this in, take the process parameter derivative, the tau derivative, then we get the derivative of the first variable with respect to, that's a mistake there, right? No, that's correct. So we take the derivative of u with respect to its first variable times the derivative of that variable with respect to tau. Okay? The derivative of the second, or the derivative of u tilde with respect to its second variable times the derivative of that variable with respect to tau. That gives us v prime. But what are these variables here? Well, it's a very simple exercise to show that this is just equal to the temperature, and this guy here is just equal to minus the pressure. Well, how do you show that? Well, remember, we defined this function as the derivative of capital U tilde with respect to capital S, the derivative of the energy function with respect to the entropy. But this is different, right? This is now the molar energy and the molar entropy. So the derivative of the molar energy function with respect to the molar entropy. Does that still give us a temperature function? The answer is it's a simple exercise to show that it is true. So that means that this is the temperature and this is minus the pressure. And so just using the chain rule, we get this relation. This is sometimes called the Gibbs equation, but it's more oftentimes, I believe, called the combined first and second laws of thermodynamics in differential form. Okay? The combined first and second laws of thermodynamics. What it's missing, however, is the chemical potential part, and that's because the molar energy doesn't depend on n anymore. It's a variable which is divided out. We're looking at this from the perspective that n is a fixed parameter. Okay, so n is a fixed number of moles. Okay, so now we have what? We have the molar Euler equation coming directly from the fact that capital U is a function that is homogeneous of degree 1. We have the combined first and second laws here. And then how do we get the Gibbs-Duhem equation? Well, the way we did it previously is we're going to insert a process path here for these variables, and then we're going to take the tau derivative of that. Okay, so if I do that, if I use this path, this process path in molar state space, and take the tau derivative using the Euler equation, well, I'm going to leave the left-hand side alone, but there are how many terms in this molar Euler equation? There's going to be two terms emanating from that when I take the derivative, two terms from this, and only one derivative from this. So I'm going to get, from taking the tau derivative of that side of the equation, I'm going to get five terms. And they are, there's the derivative with respect to that first term with respect to tau. The derivative of that second term, it's a product term. So this is just a product rule. And then the derivative of the last term produces the fifth term. Now we take the combined first and second laws, and we're going to subtract that from 5.3. So subtract 5.2 from 5.3, and this gives us 5.4. The thing that you'll see immediately goes is this term. These two terms cancel each other. These two terms cancel each other. These two terms cancel each other. And so how many are left on the right-hand side? Nothing's left on the left-hand side. We get a 0, but I get these three terms surviving on the right-hand side. Now, we usually rearrange these to put the derivative last. That's just the way it is with the Gibbs-Duhem equation. So we have S of t, that's the independent variable, molar entropy, times the tau derivative, the process parameter derivative of the temperature. Again, the process path goes in here, and that process path is a two-dimensional variable if you want to think about it like that. It's given up here. As first component is the molar entropy, the second component is the molar volume. Right, so the second term is this term here, just rearranged to put the molar volume first, and the tau derivative, the process parameter derivative of the pressure second. Of course, the minus sign comes because of the way we define the pressure ultimately. And then the last term is here. Okay, so that's the molar Gibbs-Duhem equation. I'm going to show you how this gets used. In fact, we gave a version of this last time, but we didn't show how it's used. Now, today, I'm going to show how an equation like this gets used in order to recover a fundamental relation for a material, knowing two of the state equations, okay? The equations of state. Let's do exactly the same thing, but for the entropy form. Okay, exactly the same thing, but for the entropy form. So what do I mean? Let's start with the molar version of the Euler equation. And the way you get the molar version of the Euler equation, the molar version of the Euler equation for the entropy is you start with the Euler equation for the entropy. So that is SUVN equals 1 over TS times U. I'm going to leave off the individual variables here just to make life easy, plus PS over TS times V, and minus mu S over TS times N. Okay, now all you do is divide both sides by N and use your definitions of the molar variables. Now it's still true that the entropy form of the temperature is homogeneous of degree 0. Same with the pressure, same with the chemical potential. So everything works out exactly the same. Divide both sides by N, use your various definitions, and you're immediately going to conclude with this version of the Euler equation. Okay? So, or this is sometimes called the integrated form of the first and second laws. Now, what I want to do next is derive a Gibbs-Duhem equation. So how do you do that? So let me give it to you in terms in words. So what I do is, at least for this form of the Gibbs-Duhem equation that I'm going to generate, this one should look like the previous form of the Gibbs-Duhem equation that I wanted to generate. I'm going to give you another one in a second. But let me tell you how I derive this one. I multiply both sides of this equation by the variable T, okay? This dependent variable temperature. This is the S, or the entropy version of the temperature. Multiply both sides by that. That means it gets canceled here, here, and here. And of course, we get a temperature function there, right? Now, Replace U and V with the process path, gamma tau, and then take the tau derivative. That gives you a bunch of terms, gives you an equation with a bunch of terms. Then what we need to do next is get a version of a differential form of the first and second laws. That's very easy to get. Same procedure as you did above. And so then you multiply both sides again by temperature, and then you subtract the resulting equation here from the equation resulted from taking the tau process derivative here, and you get this Gibbs-Duhem equation. So I'm going to write here, this one is an exercise to derive. Okay, it might not be clear to you how to do it. I'm going to show you with another example how this is done, but that's the basic idea. Multiply by temperature here, so you get the cancellation of temperature. Introduce a process path for the variables u and v. Take the tau process parameter derivative, both sides. Then formulate a first and second law equation in differential form. Multiply both sides of this equation by tau. Then subtract the resulting equation here from the resulting equation here, and you get Gibbs-Duhem equation. Now, it turns out I made a lot of fuss about this equation last time, but this one is not as useful as the one I'm about to derive. This one is not helpful for us, it turns out, for deriving equations. And I'm going to show you why. I'm going to show you why momentarily. But let's move on to our useful version of the Gibbs-Duhem equation in molar form. So as I just said, this one turns out to be not so useful, okay? Sad face. So let's derive one which is more useful to us for deriving equations. In fact, we're going to use this new equation to derive with some examples, derive the equations, the fundamental equations, starting with some equations of state. So how do we derive this new Gibbs-Duhem equation? Well, I thought in my last lecture I was making a mistake. It turns out, in fact, it just produces another type of Gibbs-Duhem equation, which turns out to be much more useful. And so that mistake I made in the last lecture turns out to be the right thing to do. So we're going to derive a Gibbs-Duhem equation via that mistake, which is much more useful than 5.7 above. And the way we're going to do this is we're going to start with, again, the molar version of the Euler equation, 5.6. This is still correct. Actually, this equation here is still correct. This one's still correct. They're all correct. They're all fine. It's just this one is not so useful to us. Okay? It's correct, but not useful. Start with this molar version of Euler equation, and you do like you usually do. You're going to substitute in a process path for all these variables. Okay, start with 5.6, substitute in the process path, and then take the tau derivative. But now, what I did last time was I said you have to multiply the temperature first. Well, actually, you don't. You don't have to multiply temperature by both sides first. That's only if you want to derive a Gibbs-Duhem equation that looks like what I'll call the energy version of Gibbs-Duhem. Okay, so you don't have to multiply temperature first. Let's not do that. Let's leave 5.6 as is without dividing temperature and see what we get. Well, if we do that, then we take the tau derivative of the entropy. Remember, we're differentiating an Euler equation, so we're going to get 5 terms over here on the right. What do we get? Well, we're going to get the tau derivative of this thing, 1 over the temperature. That didn't look useful to me before, but now going through some examples, it proves to be quite useful. Remember, we've got a product rule, so it's derivative of the first times the second plus the first times the derivative of the second. And we have 2 terms which are like that, one for the pressure, one for the temperature only, and then this one's a mistake here. That should be chemical potential. Chemical potential, entropy form. Right now, where's the n over here? There's no n because remember, we're starting with the molar version of the Euler equation, which has the n divided out. Okay. Now, we have this form, 5.9, one, one term on the left-hand side, five terms on the right-hand side. And now, remember, this is not what we equation that we had in deriving the previous useless or less useful form of the Gibbs-Duhem equation. But what we want to do next is pretty much the same. I want to use the Molar representation of the first and second laws. This is just chain rule. By the way, the so the first and second laws of thermodynamics is only chain rule, only chain rule. And I've never understood why it gets hyped up so much or why they give it such a important setting. I think it's because it's chain rule, but they tell you how they define the temperature. I think maybe that's or the temperature and the pressure, maybe that's the only importance of it. But in any case, the way I view it is after I get past defining the temperature and defining the pressure to be these certain derivatives, then the representation of the first and second laws is nothing more than the chain rule. So in any case, we're going to take this equation and we're going to subtract that from this equation. What terms get subtracted away? Well, these two terms are the same. This term here and this term here, they're the same. And so what results on subtraction of that is 0. The other two terms that are the same are this one and that one. When I subtract away, this one goes on the left-hand side and these two go on the right-hand side, leaving 0 on the left-hand side and these three terms on the right-hand side. Of course, as I said before, the way Gibbs-Duhem equation is traditionally written is you write these variables first and the derivative of the 1 over temperature, 1 over pressure, or sorry, pressure over temperature next. Okay, so this is the common way of writing it and the way we're going to use it. So we're going to see this version of the Gibbs-Duhem equation is going to be much more useful to us than the previous version, 5.7. And in fact, 5.7 is still true. It's just not going to allow us, in at least a certain form, of obtaining the fundamental relation by taking the derivatives or by knowing the equations of state in a certain case. And so we'll see that in a minute. Okay, so now the next thing that we want to do is go through a couple of examples to show the utility of using these molar versions of the equations to start from, or in the case where we start from two equations of state, in this case, pressure and temperature, and then we recover we recover from that the fundamental relation. But before we do that, what we're going to do is take a little break here and I'll take your questions. All right. So with example 5.2, I want to show how we can go from knowing two equations of state to reconstructing the fundamental relation for our material. Now, the fundamental relation is really what tells us everything about the material. If we know the fundamental relation, then we know the temperature, the pressure, and the chemical potential, because remember, these are just defined as the derivatives of the fundamental relation, whether we're talking about the energy fundamental relation or the entropy fundamental relation. All right, so if I view this an equation of state, I might think, well, this is only giving me derivative information. How do I obtain from it the fundamental relation? In fact, for this one, I know that I'm missing a chemical potential, right? There should be at least three derivatives. And even knowing the derivatives shouldn't get me back to the fundamental relation, right? It's not enough information. But I'm going to show you that for thermodynamic variables, it's enough. And that's because of this concept that thermodynamic variables should be, at least the entropy and the energy should be homogeneous at degree one. It all follows basically from that they're extensive thermodynamic variables. So let's suppose that we have this equation for pressure. Notice that it's in terms of U and V. So we know right away that this is going to be an S pressure. And the same with the temperature. It's in terms of U, V, and N. So this is going to be an S temperature, right? It's going to be the entropy version of the temperature, the entropy version of the pressure. We'd like to be able to recover the fundamental relation using only these two equations of state. Let's see if it's possible. Okay. Now, what we're going to do is um, I'm going to use for this first calculation, I'm just going to use the combined first and second laws in differential form. And so if I look at that equation, I need a 1 over temperature and a 1 over pressure. Now, again, I said these are entropy versions of pressure and temperature. So 1 over the entropy temperature is equal to, just have a look from this, it's going to be A minus 1/2, U minus 3/4, V to the 1/2 power. What did I do in this case? I immediately converted to the molar version of energy and the molar volume. Can I do that? Yeah, because temperature is a function that is homogeneous of degree zero. I can immediately absorb this N into the U and V and create lowercase u and lowercase v. All right. So how do I do that? Well, I'm going to need N to the 3/2 power for the top, and I'm going to need a V to the 1 power in the bottom. So let's multiply the top and the bottom by N to the 1/2 power, right? So actually, does that work out? Let's see, maybe I made an error here. Oh, no,
You mean
that's
dividing
okay.
both sides by n to the 3/3, right?
Yeah, so let's see. Let me do some scratch work. So first of all, we'll just work with temperature. So let's get rid of unnecessary things. Okay, so now we have U to the 3/4, right? V to the 1/4, and we have 1 over N to the 1/4. So what do we need on the bottom? We're going to need N to the, what we really need is N to the 1/4 on the top, right? And did I do that right? I seem to be missing some a variable. Oh, okay. Good, good, good. Should be V to the 1/2, right? That's good because I would have been missing some stuff. So now that's what I have. Yeah. So U to the 3/4, N to the 1/4, V to the 1/2. Okay. So now I'm going to need an N to the 1/2 up here because I want to divide that into V here. And if I created that, I'm going to have to add it on the bottom as well, right? So what do I get on the top? I have N to the 1/2. When I combine it with this term, I'm going to get lowercase v to the 1/2 on the bottom. This is going to be N to the 3/4. When I combine it with U to the 3/4, I get lowercase u to the 3/4 on top. Now invert that to get the temperature, 1 over the temperature, and we get this equation. Okay. All right, so good. Breathe a sigh of relief. My math seems to check out. And do the same with P over T. Why do I need P over T? Because that's the term that appears in my first and second law of thermodynamics in differential form. So there's the first and second law. It's the molar version, differential form, first and second law of thermodynamics. Okay. Now I have an expression for this equation, and I have an expression, or this term, and I have an expression for this term. Now, why did I choose to use 5.8, the entropy version? Well, because my variables here are energy and volume. And so that's the natural, those are the natural variables for this problem. So I want to have variables on the right-hand side, which are energy and volume, or I should say molar energy, molar volume. Let's plug in because now we have expressions for these two things. Okay. Let's plug in. And so what we should get is these two terms, a to the minus one half. Please check my arithmetic, and hopefully it's all correct. This term and this term inside parentheses. And then I realized that, hopefully again, the math being correct, that this is equal to 4 times a to the minus one half times the derivative. There's an error. I knew that I would get this wrong from time to time. It's not the t derivative, it's tau derivative. Okay. The derivative with respect to the parameter tau of this product. Let's check it just to make sure. So this is going to be a product rule, and I should produce two terms in taking that product rule. Okay. So the first one is going to be 1/4 u to the minus 3/4 power times the derivative of u with respect to tau and times v to the 1/2. So that's the first term. Okay, no problem there. Now I have to take the derivative. Now I rewrite this on top, and I have to take the derivative of this term with respect to tau. So what do I get? I get should be 1/2, right? Times times 2, of course. No, sorry, I want to reproduce this, so I want to use it from here. So I want to get a 2 there. Right, so what do I want? Take the derivative of this with respect to tau. I should get 1/2 times this term, v to the minus 1/2 power times v prime. Okay, so 1/2. If I extract a 4, then of course I get the 2. So it looks like it's all correct. Now, what you recognize right away is that what? This is a perfect derivative over here, and this is a perfect derivative over here. Okay, up to constants. And well, this would be a case where we'd like to whip out a nice fancy path integral to do this calculation, but it isn't necessary because I have perfect derivatives on both sides. So just integrate with respect to tau. You immediately get s. I'm going to rename this variable here in an abusive notation. I'm just going to call that s of tau, okay? And this, of course, is a constant. It stays the same, and I just get this, right? Everything's a variable of tau, of course, but I do need a constant of integration S naught. Now, how do I convert this back to from the molar entropy version to the standard extensive entropy? Well, you just multiply through by n everywhere that you see. And of course, again, I'm abusing notation here. This just means a function of what does that notation mean? So here the abuse is, just so that we're all on the same page, the abusive notation is this. All right. And again, to convert to the extensive entropy, just multiply by n. And when you do that, you should get this. Now, we should check in the end that this function is homogeneous of degree 1. All right. So that means if I put in u over lambda, v over lambda, n over lambda, that lambda should produce a lambda to the power 1. And of course it does here because I get a lambda to the 1/4, 1/2, and 1/4. That gives a lambda to the 1 power. So I get a lambda to the 1 power from that term. This term is n by itself. I get a lambda to the 1 power for that. So this function is homogeneous of degree 1. Is this a fundamental relation? Yes, it's a fundamental relation because it's a an expression for the entropy purely in terms of its independent main thermodynamic variables, u, v, and n. Okay, now By the way, so you might think, well, when you work in terms of molar quantities, then you're only working in a very specific, narrow setting. You're working in the setting where n has to be a fixed positive number. That's true. Up to this point, I'm working in that setting. But as soon as I multiply by n, I get the actual extensive version of the entropy. Now n is once again a variable of the problem. Okay, now at this point, and from this point, I'm allowed to vary n as I please. Of course, the only sensible thing to do is taking n to be positive, but I'm allowed to vary it to be any positive number that I want. This does give me the actual extensive entropy in all cases. So now n is again a variable, even though in the process of finding this equation out, I made n fixed and essentially eliminated it as a variable. All right, so that's kind of semantic jumping jacks, but I hope you get the point. This really is the full extensive entropy. And now notice that what we did in gaining that or getting that expression, we didn't need an expression for the chemical potential at all. We only needed two um, thermodynamic equations of state to get the entire expression for the fundamental relation. This is a little bit like saying if you give me a function of three variables and tell me two of its derivatives, one with respect to x and one with respect to y, that I should be able to recover the entire function. In general, this is an absurdity, but for thermodynamics, it's not a problem. Now, I will say that we've gotten this up to that constant of integration. And so, how could I determine that a constant of integration? Well, there could be some physics which help us to determine that. We're in the setting of the mathematical theory, and so we're not worried too much about that, what that constant is or how it's obtained. But there are ways, suffice it to say, for obtaining that constant. Now, let's try another method for doing this. Let's try exactly the same problem above, but this time we're going to use the Gibbs-Duhem equation to recover the fundamental relation. The way we're going to do this, and I'm not going to check all the work here, and the reason I'm not going to check all the work is it comes out to give exactly the same answer as before, so I'm trusting that everything is correct. Now, we're going to use the Gibbs-Duhem equation here to recover the chemical potential first. And then once we recover the chemical potential, what do we have at hand? Well, when we recover the chemical potential, that means we have the temperature, pressure, and chemical potential. And now if we go back to Euler equation, either the Euler equation molar form or regular form, we can rebuild the whole of the entropy or the internal energy function using the Euler equation. Okay? So using the Euler equation, if we know the pressure, the the temperature and the chemical potential, we have a full expression, therefore, of the fundamental relation. And I'll show you why this is so. Now, the Gibbs-Duhem equation that we're going to use is 5.10, and the reason why we're going to use 5.10 and not 5.7 is because let's go look at 5.7. Now, remember what the aim is to find the fundamental relation for the entropy. But this guy has, as an unknown variable, an expression for the entropy. That's not going to be useful to us. Okay, we're trying to find the entropy. Okay, and having it commingling with these other variables on the right-hand side is not useful to us. However, let's go look at 5.10 and see why this one is useful to us. This one has no entropy on the right-hand side. It does have variables u and v, and these are precisely the variables that are in our problem. So these variables are already over there with these variables, and so let's use this form. It doesn't have entropy in there. We want to find the entropy as an unknown. The way we're going to do this is, again, this is a typo here. I'm not sure, not that corrected, but this should be u over s. thought I corrected that previously. I bet I only corrected it here and then I copied it down. Okay, I think it's corrected in both places now. So what we're going to do is use the fact that we know these quantities in terms of the variables u and v, and then use integration to find this variable in here. That's how we're going to use Gibbs-Duhem in this example 5.3. So there's the equation precisely that we're using. I've solved it in terms of the process parameter derivative of chemical potential over temperature in terms of these derivatives over here. Now, I know this and this from the top, right? Here we go. So I'm just going to input those in the bottom. Now, this is where it gets a little bit tedious. So I know that these functions here and here. And so now I'm going to do some manipulations. Take the full derivative through here, and then I'm going to gather up some terms. Okay, so this is a lot of algebra, and I was shocked, surprised, and awed, I guess, that this actually worked out. But in the end, you get something like you had before, a perfect derivative. So please feel free if you're bored to check all the details here. But I believe that I should get this perfect derivative here is equal to this perfect derivative here. And so the way this works is I'm going to integrate both sides with respect to tau. No fancy path integrals required because we're dealing with perfect derivatives. And you should get an expression like this. Now I need a constant of integration. And to make it exactly work out with what I had before, I'm going to call that constant of integration S naught, little s naught. And if I do that, then everything works out precisely as it had before. And I can rewrite everything in terms of these variables. I now have an expression I meant to say the variables little lowercase u, lowercase v, that is molar energy, molar volume. Now I have an expression for this term in very simple terms of lowercase u, lowercase v. I do have a constant of integration. Don't know what that is yet, but that's fine. What I'm going to do is then I'm going to use Euler equation 5.6. Now that tells me that entropy is equal to this expression times u, this expression times v, and this expression. There's no n over here because remember I'm dividing n over n and that just gives 1. I have expressions for all of these three things. Just plug them in. So notice that the routes by getting the fundamental relation are different. In the first case, I integrated the first and second law directly, first and second law, and I get direct to the entropy. Here, what am I doing? I'm getting an expression for the chemical potential over temperature first, and then I'm using the Euler equation, and I'm reassembling. Well, I'm using the Euler equation, the fact that now I know all three derivatives and not just two derivatives. And I can get back exactly to the same expression that I had before, the same fundamental relation. So let's emphasize what we've done here, what we know. What this is saying is that if I have a if I have a thermodynamic potential like the energy, internal energy, or the entropy, and I know that it satisfies all the postulates. In particular, I know that it's homogeneous of degree 1. And let's say it's a function of three variables, independent variables u, v, and n, and I know two of the derivatives. Because it's a homogeneous of degree 1 function, that means I know the third derivative. And because it's a homogeneous function of degree 1, I know the Euler equation is true. And if I know the derivatives for a function which satisfies the Euler equation, I know everything about the function. Okay, so on one hand, I reconstructed the chemical potential and I used the Euler equation to rebuild the thing. And in the other case, I just used the first and second laws and got the entropy directly. And from that, I could find the chemical potential. How could I find the chemical potential? Well, I said once you have a fundamental relation, you can always take derivatives to find the equations of state. Okay. And so that's what you could do. So knowing two equations of state for these functions, these extensive functions of three thermodynamic variables means that we can always reconstruct the fundamental relation. Let's do another example, and a famous one at that, called the ideal gas law. So for the ideal gas law, we might have two equations of state. In this case, suppose that we have this equation. This is the standard version of the ideal gas law that you learned from high school chemistry, PV equals nRT. So here you recognize R is the gas constant. And the other equation that you might need to construct the full equation, by the way, you might have heard it said that the equation for the ideal gas law is just this. Not so. That's only one of the equations of state, and it's not the full thermodynamic description. A full thermodynamic description would require two equations of state or the fundamental relation. The other relation that we're going to use is another equation of state that relates the temperature directly to the internal energy, or vice versa, the internal energy to the temperature. So for for an ideal gas, you probably heard it said that the internal energy is linear in the temperature, but that's only true if we have a fixed number of moles. So if I have a box of gas and I have it sealed off, that means that the total number of particles inside is fixed. If I heat that gas up, okay, then my internal energy is going to go up linearly, and it's going to be proportional directly to the temperature. Okay, the constant of proportionality is given by here. This is sometimes famously called the three halves law. Okay. So with these two equations of state, we can find the fundamental relation and find everything out about this system. And how we're going to do this is we're going to use the same procedure that we did last time, and we could go either route. We could either integrate directly the first and second law, or use the Gibbs-Duhem equation to figure out what is the chemical potential. By the way, so when we start talking about statistical mechanics in lecture 9 or 10, we're also going to derive all the equations of state for the ideal gas law, but we're going to do that entirely um, from the point of view of statistical mechanics. So just uh, well, it's an entirely statistical mechanics approach. We're not going to use any other approach to formulate the equations of state for the ideal gas law. But it's very interesting to see how it comes about with very small number of assumptions, and the power of statistical mechanics can build the whole theory. In any case, we're going to put the equation of state in these two forms. One for 1 over temperature and the other for the pressure over the temperature. And if you convert these to the molar versions, then we have 1 over the molar temperature is equal to 3R over 2U. And the pressure molar, or the entropy version of the pressure, entropy version of the temperature, molar forms, is equal to R over the molar volume. So now we're going to use the same process that we did before. Gibbs-Duhem equation. Here's Gibbs-Duhem equation. We now know these guys here. Of course, you have to imagine letting U and V being functions of tau, right? That's all that's really required there. So you put those two forms in here and here. So that's there and there. I pulled the constants out. And this is nice because they're both of the same form. It's going to be constant times 1 over U and constant times 1 over V. Okay. Or just constant over U, constant over V. Pull those out and we just get this. Now, the form here is very simple. If I take the derivative of this object here, what do I get? I get U prime over U. Okay. Because, well, what is the derivative of this? It's going to be minus u to the minus 2 power times the derivative of u. I get a u uh, over u squared. That just gives a 1 over u. And so I get this term or same procedure for the derivative involving v. But again, this is a perfect derivative here, right? This is a perfect derivative. This is a perfect derivative of what? So it's a derivative of a log. Okay. So remember, if I take log, how do we do this? We take d tau. I'm probably beating a dead horse here. U tau. It's going to be 1 over u prime tau times u tau, right? Nope, no other way. And the same with v. It's a perfect derivative, except that you have to be a little bit careful. Now we're in the realm of dealing with things that have units, things that have units. So I can't simply take the log of something with units. It's meaningless. I can only take the log of something which is unitless. And so that prompts me to divide. So that's very simple. Take this variable here and divide it by u naught and divide the same by u naught. Okay. What does that change? For the derivative, nothing. Nothing has changed. Do the same with v. Divide by v naught and divide by v naught. What is v naught? What is u naught? It's anything you want, actually. So we're going to call it a characteristic molar energy and a characteristic um, molar volume. They can be anything that I want. They do have to be positive because I can't take logs of negative numbers. Okay, so introduce those. Now it's still perfect derivatives in sight, and I can take the integral of both sides. We do get a constant of integration, actually, in addition to those two constants that we just introduced. The constant of integration, I could call that an S naught, as I did before. I'm going to call it mu naught over T naught. I'm going to combine this with a few other variables in a moment. But in any case, when I integrate these perfect derivatives here, I get two log terms. One is the log of an energy, and one is log of the volume, or I should say molar energy, molar volume. And again, these were introduced purely so that I could take a log of something without having problems with units. If you want, you can check this. Just take the derivative with respect to tau of this thing, you get right back to here, and the derivative with respect to tau, that one gets you right back to here. So nothing, no harm, no foul, right? Okay, so when we did the integration, this gives us a constant of integration. Right. So now we have more or less a full expression for this. We can go back to the Euler equation because we have a chemical potential term. So I'm going to use the molar version of the Euler equation, and I'm going to plug everything in and see if we can't produce something which is in some way sensible. So for our temperature term, the 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 U1 over U cancels. For this term, the V1 over V cancels, and so I get these terms here, which are just constants. These two terms here, or let's see, am I getting that right? Or yeah, just the only thing that I get a log from is this term here. Okay, so that gives me this, and that after my integration. I guess I should have called that, is it yeah, it is minus. Okay, or is it? No, let's see. I think I made a slight error here. I think I've got a sign error on this one. If I want this to come out with a minus sign here, um, oh, actually, I can fix it just by putting a plus sign. Okay, no problem there. Okay, cool. Now I'm going to collect all three of these terms together, and I'm going to call that S naught. I'm going to combine my logarithm terms together, and what I get here, remember, logs, the sum of two logs is the log of a product. I can take this 3/2 and put it in as a power here, which I've done, and this gets no power. Leave the R out front for units. So this is a perfectly good and fine expression for my fundamental relation. Now, how do I get back to the fundamental relation that involves U, V, and N? That is, how do I go from the molar version back to the standard version? All you do is multiply by N. That's it. Okay. So if I multiply by N, I've got to take care of that multiplication out here and out here. And I want to convert these variables back to variables that are in terms of N. How do I get there? Well, you just use, so U was defined as U over N, right? And so N times, let's see, how do I get there? Right. So I just have to, yeah, I do the same process that I thought it was going to be simpler than that. It's not. So you have to introduce the right number of, gosh, deleted some of my equation there. There we go. So what's the procedure here? I just have to introduce the right number of powers of n in order to clean things up here. I'm running out of time, so I'm going to leave it up to you to figure out how to do that. I've introduced also a units for the number of so let's see. I think the way I did it was I defined this quantity so that little u is equal to u naught over n naught, and I use the same normalization here. But apart from those two things, you should be able to figure out how to get from here to here. Oh, yeah, I guess I listed it down here. So what's and then of course I have to fix up my constant. All right, so I'm going to leave you to check out those last few details. This is the fundamental relation though, after you've checked out those last couple things for the ideal gas. So this has a famous name. You can Google it right now. I'm blanking on the name. I'm not sure I could pronounce it. It's a little bit um, uh, non-standard American English name, and I'm only good at that. So it has a special name, but in any case, what it is the fundamental relation for the ideal gas. Okay, so if I have this relation, then I can derive all the other thermodynamic variables of the system: the temperature, the pressure, the chemical potential. Now, so you could take this and see if I can derive the PV equals nRT PV equals nRT ideal gas law relation that you're so familiar with, or the three, what was it, the three halves law involving U or temperature. So you should be able to get back these. But in addition to that, you're also going to get an expression for the chemical potential, which we found was here. So I had two or three examples where I'm showing you how to use these Molar Euler equations and the Molar Gibbs-Duhem equations to start from equations of state and get back to the fundamental relation, even if I'm missing one of the equations of state. So that's the power of these thermodynamic relationships. So with that, I'm going to stop and I'll take your questions.